Hi, it's Rick here again from Renaissance Charge. Remember, with Renaissance, going green saves you money. So we're going to look again at another kit here, which is the mini window motor kit. Now, of course, we've made this a little bit more than a mini. Here we're looking at a lot more coils here, or a lot more wire at least. And let's go over the details. So again, let's look at the schematic. That's not even a schematic, but basic instructions. What we've done is we've added 3 more coils with no trigger wire, and we've added thicker wire for the motor windings. So instead of 26 here, we still have the 29 on the trigger coil on the top, but instead of 26 we have 19 gauge wire, and then the 2 other coils on the bottom are 19 gauge wire as well. So we put as much on there as we could put on, and again, we've beefed up the transistors to the MJL 21194G, and we have 3 amp diode instead of 1 amp, and the neon bulb does have the little resistors in series with them. Let's see if I can get a close up here. You can see those 4.7K resistors, the ones that are going upright, the lighter blue ones. They're in series with the neon bulbs. So we have transistor pads too on this with thermal grease. When we assemble the kit or the circuit board, it comes with this bracket, this L aluminum bracket that we tap and die and put in all the hardware connected to the board. So that does provide significant heat transfer for keeping these transistors cool if you're really going to push this thing, especially when we go up to like 24 volts. I can't imagine doing that with this thing at this point, because it's already going to 16,500 RPM, pretty fast. So again, we've provided also the base plate for $15 extra if you want to buy that. So the kit on the website r-charge.net is under the what we call the window motor, small window motor kit, and there's 3 different options there for one basic, the basic system as we noted here on this page, or adding more coils as we showed in this model right here the other day. And that's option number 2, where you have all 3 coils there with a smaller circuit, and now we offer this circuit with bigger components, bigger wire. So let's take a look. One thing I want to notice is that there are 6 magnets. They're neomagnets, and they are pointing in the north and south direction. And so we're only firing with this circuit off of the north pole, or if we flip the coils the opposite way, we'll be firing off the south pole of the magnet. So we're only using half of the potential of this motor. When we use the full sequential circuit, as we call it, the bipolar circuit developed by John Bedini, we have the ability to fire off of both poles, so then it would be twice the power. So we haven't provided that in the kit, but you can buy the circuit by itself and add it to this if you want to do that. The only thing is we don't have the timing either on the front end yet for Hall switching or reed switching or whatever. You'd have to put a little timing disc on there and mount it somehow, or you could actually fire off of the magnets themselves. It's a little bit trickier that way when you try and do that. So let's look at the voltages here. The charging voltage, which has gone up from doing some runs last night on this, and a little bit right now. You can see it's slightly coming down because I ran it a little bit about half an hour ago. And so 12.4, 12.05, and then the input is 12, 27, 28. And we're going to look at the amp meter here, and it's a 3 amp meter, so we can take it about 1.5 amps, or between 1.5 amps and 3 amps here. And if we notice the trigger resistance here on the board, we're running 10 ohm resistors on each of the base resistances in the circuit, and that would represent this resistor here in the basic schematic of the one circuit diagram, and this is the 3 circuit diagram. This is the same setup we have here. Again, these are 10 ohm right here. These are the base resistors instead of being 220 in this diagram. So what we're going to do out here is play around with the resistance. I do have a bulb here just in case I do go too low. That bulb will come on and act as a servo sort of to the system. But instead of having a pot here right now, I'm running different resistors. I'll mention that as we run this. The difference right now, I think I'm going to run it around 100 ohms is what it wants to be, around there. So between 80 and 120, I think this wants to run it at this particular voltage, which is 1227. So as I go up in voltage to, say, fully charged battery, say 12.7 or 13 volts even input, then what's going to happen is the resistance will change a little bit because you're adding more power to the system, and it's going to spin faster. So there's going to be a little bit different sweet spot, and that's what the bulb is for too, to make that more regulated. As the voltage changes, you still maintain more of a sweet spot when you use a bulb. So the other thing is, if we go up to 24 volts, it's going to be considerably different. It's going to push a lot more current here. It's going to double at least the amperage input. So we'd have to watch the temperatures and all that if we do that. Once you start going above 1 amp on these devices, then you really have to start paying attention to the heat. I think we can go comfortably to 1.5 amps per transistor with that heat sink without it getting thermal runaway on us and having to cool it with a fan or something. The transistors are capable of 16 amps maximum under 20 volts, and as you go higher in voltage, that goes lower the amount of amps you can push. But you really have to consider the pulsing in this system for what the actual amps are at a particular point in the process. So really comfortably, even with fan cooling it, you don't really want to go above too much more above 3 amps per transistor. You have to really watch the heating or the cooling in that circumstance then. So I mean, I've taken them up to the full amount, but you just have to watch it in a pulsing system like this. So let's look at this a little bit. What we have is the trigger wire from the top here coming out to this wire here, going to this bulb, coming around. What we have on it right now is a 100 ohm resistor, and I'm going to attach it to either of these 47 ohm resistors, and there's a 10 ohm resistor. So we have a variety of resistors here. So let's start up with directly 100 ohms on what we call the final resistor, or you could consider it a branch resistor. And again, we have some tape on this shaft here so that I can attempt to look at the RPM. So you can see the amps sitting at around 2 amps right now. And so let's look at, you can see the charging rate already is picked up. We're at 14 14,000 RPM. 14, it will go up to about 6 with the right resistance. So you can hear that one a little bit faster. But we also want to consider what the charging rate is. See, that was a better charging rate when we went up there. It's hard to get this right on here. 14.6. I had it at 1600 RPM. See there, we're making it go faster here, and you see the amps went down to 1.5 amps almost. And now we're up to 16,000 RPM. And that's saying 15. So we might want to try here. See, that didn't work. See, now that went even faster. So now we're down to 1 amp, but we're really 17,800 RPM. 18,000, well, I would say, if I can get it right in the right spot here, well, 18,000 RPM right now. And what's the charging rate? See, the charging rate has come down a little bit, and that's where it's really finicky, the system. Depending on how you shape the coils, I could push them a little bit closer, but it's a little bit of an obstacle to try and position these coils as close as you can to the rotor without having it rub against the rotor by bumping it or something. Again, if you're going to go this fast, you better put the string tape in the crazy glue and don't stand in the direction of it like I am doing right now. If that magnet breaks out, it will fly like a bullet and go right into your head. So you're responsible to be sensible along those lines. So again, we're not charging as fast now, but we're also not drawing as much power. We're at 1 amp right now, and now we are still charging the batteries, as you can see. So let's look at the thermal. 70-degree temperatures, depending on where we place it in there. Let's look at the diodes. Well, always look at all the components. The resistors are the main thing that get hot, but the transistors are the most important to watch for. And you want to look at the coils too. You don't want to have a meltdown in your coil. See, this coil right here could be pushed in a lot further, but I don't want to rub against. So it'll be this resistor right here that will be the hottest. And it's not that bad. It's about 135. And this one right here is 155. Well, it's climbing. So we really could use some more higher wattage resistors here on the final, and that's what we'll try and put in the kit here, and give a variety of resistors to play with. You can take those resistors up to about 300 Fahrenheit before they really start discoloring and melting down on you. But you'll start to smell them at around 200 Fahrenheit. So you can play around with that. If you use a pot, you want to really use a big pot because it will tend to blow out the pot. I blew out one of these little ones on that last test that we did on this motor over here because I was turning it too fast while it was running and it just blew it out. So that's only about a 3/4 watt pot, and these are 2 watt resistors, and they're already getting significantly hot. So again, if we use the right bulb, we could actually get away with running just a bulb on there and no resistors. and the bulb I have on there is pretty high wattage, so you're not going to see that come on, and it's not suitable for this arrangement to run on itself. So we could further play around with these resistances and see if we can go even higher. So we could add another wire here, for example, to the whole string, and see if didn't make much of a difference because that was only a 10 ohm resistor. I mean, it's hard to see if it didn't really make much of a difference, but yeah, it went up 200 RPM by doing that. So we can still play with this and spin it faster, but the charging rate and the amp draw will go down. And there's a limit, obviously, to how far you can go. So now we've got another 47 ohm resistance. See, oops. So that didn't make much of a difference. So altogether we have 100 ohms, 220 here, 220, 100 ohm, and a 10 ohm resistor in series with each other. And the thing about this is, as you play around with these, you'll see it's not easy to actually figure out all the relationships here. You can add now some resistance in parallel with the whole amount, like a larger resistor. For example, it's 470. You can play around with it. And see, that didn't work. That brought it down too low. But sometimes it can have a dramatic effect. I don't need to get into that right now, but what else do we have to talk about here? It is charging batteries, and it is quite powerful. You can see it does draw more current as I slow it down on this particular setup. It's not like the monopole, where the monopole will do the opposite. Because we are dealing here with what we call positive or regular current in this system, more than what the monopole experiences. And so it's kind of burning my hand when I try and stop it. I can stop it if I really want to, but it's going to burn my hand. Ouch. So yeah, we're talking about 12 watts here, charging, and a lot of torque. Ouch. If I take maybe a paper towel and try and stop it, I can. Ouch. It burned me. So you can look at the shaft temperature while I'm doing that. Ouch. Yeah, 100 degrees of my fingers. It is hot. It is real power. Now, if we want to go up in voltage to this thing, let's see that. Ow! That resistor is also very hot. See that one, 168. So now let's go up in voltage here to 24 volts and see what happens. So we're going to move the charging. Oops. Oops. Didn't want to do that. Let's try and move this all over without upsetting too many things. If you don't mind, I think I'm going to use another wire. Hopefully this is not a burned out wire. Oh, see, you don't want to do that. Okay, so now we're going to change this to 24 volts, both of them. And then we've got that, so 23.9, that voltage is at. And then we're going to come around here. And then we need one more wire to connect these two batteries up to each other. Alright, so everything looks good. Let's see the amps. Here somehow. So you'll find that sometimes if this is in the right position, it will actually self-start. But it can go in either direction with this circuit. When we use the Hall switching, and that generally only goes in one direction, the way you time it. So this is going to go very fast. So I think we're going to have to change all of our resistances here. So I'm going to add another 470 in the line and play around with it. It may destroy. It may go so fast that it blows out the magnets. In which case I have to be careful that I'm not standing in front of it. So again, we're at 24.3 volts to start on the input, 23.89 volts on the charging side. Make sure that all the charging sides sufficiently attached. And because we have so many windings in the center here, we started before we paralleled the wires together. It makes it a real easy start because it only takes a little bit of voltage to turn the transistors on. So I think we are, see now we're too high. So now we have to actually come down a little bit to start it. Just to get it started. Actually, we're going so fast, I want to put a face mask on. Because I don't want to get hurt. I'm going to put this on here. Don't laugh, that's me. But we're going pretty fast. So again, what I did is I started off by bypassing the 470 ohm resistor, and then once it got up to speed, I could then transfer over to it. So let's take a look at the RPMs and all the numbers. Wow, that is fast. $26,500 RPM. Wow. Two and a quarter amps. 26.6. And let's look at our heat. I think we're a good 70, 80 on the heat. 70, we're okay here. We're 1 amp yet on each of these transistors, so they're still cool enough to not worry about. So the tape is holding out so far. Like I said, without the tape, I was blowing this out, I think, at 30,000 RPM. Coils are okay. Now if I attempt to stop this, there's no way I can stop that. I'm burning my fingers. So isn't that a cool motor? So let's look at it again. $26,500 RPM, and we're already, the batteries are discharged because we're already past the C5 rate of discharge on these batteries. Can only do, the C5 rate is around 2 amps, so we're pushing these batteries lower. So you want a bigger battery, and then if the voltage was higher, we'd probably be seeing more like 28, even 2,900 RPM on a fully charged 24-volt system. That's fast. That's incredible. So again, looking at these 416 Fahrenheit. That's the 220 ohm resistor. This one's 251 Fahrenheit, and that's the 100 ohm resistor. So as those resistors heat up, they change in value. So that's why you want a bigger resistor, like the at least 5 watt, maybe a 10 watt resistor, maybe even the 50 watt resistors we provide with our big kits. So you can see it's sufficiently charging of the batteries. Is that the sweet spot? That remains for the customer to figure out. Sweet spot being the fastest charging rate for the lowest amp draw and the most desired mechanical power. If you don't care about the mechanical power, you might just be interested in the fastest charging rate for the lowest amp draw. For me, I calculate all 3 of those factors because I like the torque. I like to use that torque. Now this is not showing you what we did in our earlier video of powering a fluorescent light bulb, which we did over here. Let's look at this arrangement over here. Is where we did the first, that's actually the rotor that I took off of this earlier system, but we were powering this off of a sort of a boost system, but it uses a car ignition coil to boost up the voltage, and then you can actually power the fluorescent bulb. We were doing that with milliamps of power if you look at my earlier video on it. So we could light up a whole bunch of fluorescent light bulbs at the same time charging these batteries up, and then providing a lot of mechanical power. And the fluorescent light bulb would not diminish the mechanical power, sometimes it even enhances it, and then it may or may not interfere with the charging rate as well. So we can have free heat. We got quite a bit of heat here. 400 degrees, as we looked at, 412. And we could produce heat here. We could produce heat in the coils if we want, and in the transistors, and while we're charging batteries. So then, of course, we could charge bigger batteries than what you see here, instead of equal-sized batteries. And that's another whole element, as we've discussed in other videos. So I'd say that's pretty impressive. I didn't know what RPM I'd be getting out of this, but we could take this up to 36 volts. I just don't have all those batteries lined up here at this point, and I'm afraid that I'm gonna have to do it another time. I think that would be fun. Probably blow it apart. But I'm surprised we got no vibration that is moving this thing around. It's holding. This weighs a couple pounds. I would say each coil is probably a pound each. So you're looking at about 3 pounds, maybe more. I'll have to weigh it out. I'll put that on the product page later on. But I think it's pretty impressive motor there. Alright, I think that's it. What else can I say? What I've done here is I've tied each coil together. Beyond just tying it to the center shaft here, support shaft, on each one of them, I've tied them to each other and pulled them in so that you can see, we still have some more room there that I could get a little bit closer. So there's a lot more things we can do, but this is just showing you the basic system. Again, this is only 1/2 of the potential of that motor. If we were to use the other circuit, we could get double. That circuit's got quite a bit more transistors to it. There are 6 transistors per circuit. So here we only have 3. So that's quite a bit more of a circuit board. Now what you could also do is you could double up the transistor, or sorry, double up the coils here, and so have, instead of this being 1 wire, you could have 2 wires in parallel, and then you could have a board like this, where you're running 6 transistors on the system, and that would double the power. The less wire you have though, the less charging benefit you're going to get out of the system. So we try to put as much wire as we could really fit on there. I mean, this is a little tiny kit, but look what we've done with it. Made it really big. What else can we say? So again, this is almost self-starting. I hope you've been able to hear what I've been saying this whole time, because that was rather loud. But this is almost self-starting here. You can see, even when at low RPM, I'm still... Okay, so... So we could put... Yeah, see, I can't even stop it. So you can see the voltages are coming back to what, stabilizing again. Anyway, when we have the Hall switching and all that, you can have self-starting. As soon as you turn the power on, it will just start right up and go in one direction only. But here you can have both directions. So let's look at this rotor that I put together before. You can see it's not anything beautiful, but it is holding out. I don't see any broken magnets in there, I don't think. Actually, that may be. Let me see this for a second here. I've got quite a bit of string tape on here. This one feels like it may be cracked. Right there feels like it's maybe broken out. Yeah, I think it's broken. So, I mean, we're only, going to use this for 12 volts really, but you can see what 24 volts does to it. So again, with Renaissance, going green saves you money.